Hello YouTube, I'm going to be giving a presentation over fields, and my goal here is threefold. I want to examine and build a basic definition of fields. If you don't know what they are, we'll discuss them. I want to take a step back from fields and discuss a special type of ring which will eventually relate it back to fields, so if it's not immediately clear when we're discussing it why we're doing it, I promise I'll take it back. And also to discuss extension fields. So if you don't know, let's take a look at fields as a definition. So similar to rings, it is a set of elements on which two binary operations are defined. We call these operations addition and multiplication. So what kind of properties do these two operations have? So under addition, we see that the elements are closed, associative, identity, have inverses, and are commutative. So what about multiplication? Notice here that for multiplication we remove the zero element, the additive identity, because, well, it also needs to be a group under multiplication, and that zero element can sometimes give us some trouble. Remember, of course, that we need some way to link them back from rings, so the distributive property also has to hold. Now, we call them addition and multiplication, although they don't always have to be addition and multiplication. They can be, different ways of operating the elements together. However, for the purposes of this presentation, we're going to think of them just as addition and multiplication, as we all know and love. So let's take a look at some examples of fields. First off, maybe the most intuitive and obvious example is the real numbers under addition and multiplication. The integers mod 3 under addition and multiplication. Maybe not as intuitive, but also a field. The rational numbers under addition and multiplication. The complex numbers under addition and multiplication. And let's take a look at one non-example. One non-example is the integers mod 6 under addition and multiplication. So it may not be apparently clear, hey, the integers mod 3 was a field, so why can't the integers mod 6? Let's look at that. I'm going to pick an element 3, and remember that we need inverses in a field for any element to take it back to the identity. And if we operate it with any other element under multiplication, we'll notice that, hey, we never get back to 1 here. So since 3 does not have an inverse, the integers mod 6 can't be a field. So as I said earlier, we're going to take a step back and we're going to look at a special kind of ring. But before we do that, we're going to need a definition. And the definition is this. It is zero divisors. Zero divisors are when two non-zero elements are operated and you end up with 0. So it may not be clear when this might happen. We're sort of so used to operating in the real world, or in the real numbers rather. And so let's take a look at an example. Well, you've actually already seen an example of when this happens in the integers mod 6. I picked one such example, our good old 3 again. 3 operated with 2 equals 6, and 6 mod 6 is of course going to be 0. So that's sort of one example of where you might have zero divisors. So an integral domain is any commutative ring with identity that has no zero divisors. So we're just talking about fields. Let's relate this back to fields. There are several interesting relationships between integral domains and fields. For instance, the law of cancellation holds in an integral domain. Well, not related to fields yet. But every field is an integral domain. Hey, that's relating it back. Every finite integral domain is a field. And the ring of integers mod p, where p is prime, is a field. So all these are provable. You can work through all of these. I actually want to focus on 2 of them in my presentation. The law of cancellation holds in an integral domain, and that every field is an integral domain. And to prove every field is an integral domain, we'll need the law of cancellation. So let's start there. Law of cancellation, if you didn't know, is written like this, that let R be a commutative ring and A, an element of the ring, is non-zero, then R is an integral domain if and only if A operated with B equals A operated with C implies that B equals C, where of course A, B, and C are all elements of the ring. So I'm going to prove this for you. It's an if and only if proof, so we're going to have to go both ways. Let's examine the first way that I want to go. I'm going to assume that R is an integral domain and assume that AB equals AC and that A does not equal to 0. And of course, A, B, and C are elements of the ring. And we have to show that B equals C. So remember, we're in a ring, so we have additive inverses, and so we can subtract over AC to end up with AB equaling AC. We have the distributive law, which of course holds within a ring, and so we can rewrite this as A times the quantity B minus C. Since by assumption A does not equal 0, B minus C must equal 0 since we're in an integral domain and we have no 0 divisors. So therefore B has to equal C. Now let's go the other direction. We're going to assume that R is a commutative ring, assume that A does not equal to 0, and we're going to assume that AB equaling AC implies that B equals C, where of course, again, A, B, and C are elements of the ring. So we're going to begin by saying that sum A operated with B is going to equal 0. And we have to show that R is an integral domain. This means that AB does equal A times 0, since AB equals 0 by assumption. So that means that B has to equal 0 here, just by matching up our different numbers. So we just proved that in an integral domain we have the law of cancellation. So let's do that other proof that I was talking about. I want to prove that every field is an integral domain. This one's kind of almost follows directly from having the law of cancellation, but I'll show it to you anyway. Let F be any field and AB equaling AC, where A, B, and C are elements of the field and A is non-zero. Since we're in a field, we know that the multiplicative inverse exists. We can multiply it on both sides. Therefore, we have B equaling to C right here. And then by the previous theorem that we just proved, the law of cancellation, F is an integral domain. So we've shown that every field is indeed an integral domain. So the next topic that I want to talk about is extension fields. Put it very, very plainly, it's a small field contained in a bigger one. We sort of note that by using the greater than symbol, although it's not exactly uniform. Some texts might use a slightly different notation. And so let's take a look at some examples and a question. The complex numbers are an extension field of the real numbers. So remember that the complex numbers are written as A plus BI, where A is a real number and B is a real number. So since any complex number, you could have B with the coefficient of I be 0, you've got all the reals in there, plus you've got the imaginary numbers as well. So the real numbers are an extension field of the rational numbers. Hope you can see that pretty easily. And the mitigating example is, let's say that we're in the field of rational numbers, but we really want the square root of 2 and anything else needed to make that a field. Does that create a field? Well, if you just add the square root of 2, I hope that you can see that, well, that's not going to make it a field. You're going to have a whole bunch of problems with inverses and closed and all those kinds of things. And this creates a whole new field of study called algebraic number theory. So let's take a look at this a little bit deeper. The extension field, as I mentioned, adding in the square root of 2 and all the things it needs to keep it a field is called the rationals. Rational numbers are joined with the square root of 2. And I claim that all things in this field can be written as b plus the square root of 2, where a and b are in the rationals. So let's examine my claim really quickly. And in order to do this, we're going to have to depend on our algebra knowledge. I'm going to pick an element 1 over 3 plus the square root of 2 and show that it has an inverse, or that it can be written in the form as a plus b times the square root of 2. So we use our algebra, our conjugates, in fact, to show this. And the mathematics is pretty simple. We eliminate any irrational numbers in the denominator and come on down here, and we end up with something that can be written as a plus b times the square root of 2. And it's not terribly difficult to show this in general. So for the most part, you replace your 3 with an a and throw a coefficient in front of the square root of 2 and show it in general. We can show that that indeed we can write this as something plus something times the square root of 2. The only part that might take a little bit of convincing for you is whether or not a over a squared minus 2b squared is indeed a rational number, but I hope that you can see that a squared is a rational number, and you're only subtracting away 2b squared, which is also a rational number, and a rational divided by a rational is going to give you a rational number. So that about wraps up my talk today. I will end with that. How do fields help us? Well, they help us understand a little bit more about Galois theory, which is sort of the way that you can start to examine finding roots of polynomials, and building up basic definitions of these fields is going to help you understand that. So, hope you enjoyed my talk, hope you learned something, and